Hello everyone, this is Mr. Kaviani, and in this video, we're going to take a look at the kinematic equations. By the end of this video, you should be able to use these equations to solve problems for any value related to the motion of an object, and you should be able to graph the position, velocity, and acceleration of an object using these equations. Before we jump into the kinematic equations themselves, let's take a look and remind ourselves what we know so far. We know that the relationship between velocity, displacement, and time looks like this. The velocity of an object can be represented as the change in its position or its displacement over time. And as a reminder, this change in position means the final position, xf, minus the initial position of an object, and that's again all over time. We also know the relationship between the acceleration of an object, its velocity, and its time, right? We've defined acceleration as the change in velocity over time. And this change in velocity, again, is defined as the final velocity of an object minus its initial velocity over time. We can take these two equations and rearrange them and combine them to get some really useful relationships that relate velocities, accelerations, times, and displacements. Let's take a look. There are three kinematic equations you'll need to know for this class. Now, these are given to you on every exam, including the AP Physics 1 exam. So you don't need to memorize these, but you should know how to use them and when to use them. Now, our first equation looks like this. And the derivation for these you can find separately. For the sake of this video, I'm just going to provide you the equations here. The displacement of an object is equal to its initial velocity multiplied by the time plus 1/2 its acceleration times time squared. So this equation relates our initial velocity, our displacement, our acceleration, and time. And so given any three of these variables, you could use this equation to solve for the remaining. Our second equation looks like this. The final velocity of an object squared is equal to its initial velocity squared plus 2 multiplied by its acceleration and then multiplied by its displacement. And so this equation relates our initial velocity, our final velocity, our acceleration, and our displacement, delta x, but it does not include time. So given any of these three variables, you could use this equation to solve for the last one. And our final equation looks like this. The final velocity of an object is equal to its initial velocity plus the product of its acceleration and the time it's been accelerating for. And so this one relates, again, our initial velocity, our final velocity, this time acceleration and time, so it does not include displacement. Now, you'll notice that each of these equations is missing something. You'll need to think about what equation to use based on the information that you're given and what you're looking for. And we'll take another look at that when we get to our problem-solving process. Now, just to define each of these variables so it's clear, our initial velocity is going to be defined as v initial. Our final velocity will be defined as vf with a little subscript f there. Our displacement we can represent with a delta x. And remember, this is actually just xf minus x initial, where x represents our position. Acceleration can be represented with an a, and time will represent with a lowercase t. Now, we don't use delta t, just in case you were wondering. We usually set our initial time to be 0, and so in this case, this does happen over a time interval, but we represent that time interval just with the letter t, which is essentially t final, but because t initial is always 0, we don't really show it that way. We just call it t for time. There you have it. These are our kinematic equations that we will use throughout the year. Now that we have some equations to represent motion, I want to revisit our motion graphs from earlier to get a deeper understanding of what these look like. For non-zero acceleration, meaning some positive or negative acceleration, you'll recall our position versus time graph looks something like this. Let's say that's for a positive acceleration, okay? Our velocity versus time graph then looks something like this. And again, this is only for the positive acceleration case. If you'd like a refresher on motion graphs, please go back to the previous video on graphs of motion. Now, we understand that the position time graph looks to be some sort of quadratic, and our velocity time graph is some sort of linear relationship, but now we have an equation that we can pair with the graph to understand it better. We know that the displacement of an object is equal to its initial velocity times time plus 1/2 a times squared, right? That's our kinematic equation. Well, I can even break this apart and just move the initial position to the other side. xf would be vit plus 1/2 at squared plus the initial position, right? If I take this delta x and split it up, into xf minus xi, and then move the xi to the other side, I get a function of position, right? This is position really at any time. So position is proportional to time squared. So if you're ever asked to construct a detailed graph of position versus time, you can use this kinematic equation right here, this quadratic equation. You can plug in your acceleration and initial velocity and time, time is your x variable in this case, and you can construct a graph of position versus time, and now you understand why it's a quadratic. Then for the velocity versus time graph, we know that our final velocity is equal to our initial velocity plus a times t. That's our third kinematic equation. Well, hopefully this looks a lot like the form of a line. Y is equal to, this is b in this case, plus mx, right? So this is the slope-intercept form, y equals mx plus b, where acceleration is our slope, right, our m, and the initial velocity is our y-intercept, and then of course time is our x variable. And so now we have a reason to understand why this is a linear relationship as well. Now, when you have a zero acceleration, as in there is no acceleration, we have the same equation to represent our displacement, right, at any moment in time. However, this last term goes to 0. And so again, I'll split up the delta x here. The final position of that object is just VIT plus its initial position. Again, if you split this into xf minus xi and then move the xi to the other side. And so we have a linear relationship. This is our y in this case. VIT, this is our mx plus b, essentially. So the initial position is our y-intercept. The slope is our velocity, right? This ends up being our slope value. And time is our x variable. This is the equation that we came up with in the buggy car lab. And so you'll probably remember our graph looks something like this. I'll draw it at some non-zero starting position for a positive velocity in this case. And so again, this looks familiar, also linear. We have a reason to understand that it's linear. For a velocity time graph, the VF equals VI plus AT equation the AT term ends up going to 0. And so we just get VF equals VI. It's not very interesting, but it essentially means that our velocity is just some constant value the entire time. And so on the buggy lab, this was something like 46 centimeters per second, and it didn't change, right? Our final and our initial velocity, it's just velocity the whole time. So we can really drop the initial and final subscripts. When you don't have acceleration, your velocity does not change, so you don't have to represent that way. So there you have it, motion graphs revisited with your kinematic equations. If you're ever asked to construct a detailed graph, you can use these equations, you can plug in points for time into these equations and then plot them appropriately. I'll introduce our problem-solving approach then using these equations. I'll go into much more depth on this in our next video, but just to share with you the acronym that we use, DGEpsi is a helpful acronym to remember the steps that we use to solve problems, to break them down into small components and logic our way through. The first is D, that stands for diagram. We'll draw a diagram. This is not only a sketch, but this could also include motion graphs, so it doesn't have to just be a picture, but it can also be a representation of that object's motion in a motion graph or some other kind of diagram, okay? Our G is our given information, so I'll say given info. These are things like known quantities, essentially. You could also include in this area constants, anything that you're already familiar with about the problem. Our U is our unknown. So in other words, right, what are we solving for? Can you identify the variable and maybe a symbol for the thing that you're looking for? Our E are our equations. So these again are just one type of relationship, but what equations can we use to relate the things that we do know to the things that we don't know, right? So relates given to unknown. These are our tools essentially. This is our toolbox. Now, the P in DGEpsi stands for plan. So before we just jump into problem solving, we need to take some time to plan our approach, right? What equations are you going to use? We need to plan our order, right? And our steps, so we have a really clear logical solution. Which brings me to S, which is our solution. So the actual problem solving, rearranging equations, plugging in values only at the very end, right? So you'll always rearrange equations first, right? Rearrange your equations first, plug in at the end, super critical, just to avoid having a very messy solution and making routing errors on the way to our final answer. And that brings us to A, which is, again, our answer, which we won't just write, but we'll also evaluate. We're going to evaluate our answer. Does it make sense? Is it the right sign? Is it the right magnitude? Did we include the correct units? So again, taking some time to reflect on our answer. Okay, now please take a look at my next video where I go into depth about the DGEpsi process with some example problems.